Okay, so today we're gonna look at the functions of bounded variation. So what's the goal here is to do the equivalent of what we did for positive measure, that is to construct a Borel measure on R. So remember that for positive measure, how we did that, we could construct, so we would take an increasing function that is right continuous. This is important so that the measure has has the continuity property. And we define mu of AB as f of B minus f of A. Okay, and then we extend the whole Borel set by Carré-Théodori. So that was easy. And remember that also conversely, if you have a measure on RBR, it determines a right continuous increasing function just by taking, say, the measure from minus infinity to x, if it's a finite measure, for example. But this correspondence is unique up to sheaf just because I'm looking at the difference of the function. So sometimes you have to normalize things. For example, f of minus infinity is 0. So it's the same setup as before, except that now we want to construct not a positive measure, but we want to construct a sign measure. Okay, and the key to do that is to look at functions that do not oscillate too much. And those are the function of bounded variation. Okay, and interestingly, okay, so this would define, so we would like to define a sign measure on RBR, and once you have a sign measure, you can integrate on it, right? So we know how to integrate on measures and also on sign measures, just integrate on positive minus the negative part. So we can construct an integral once we have a measure also, obviously. Okay, so what do we mean by a function that does not oscillate too much? And for this, we need the notion of total variation of a function. It's very close to the notion of total variation of a measure. It's actually the notion of total variation of a measure is a generalization of that. So what is it? So you have a function f, it's actually big F. Oops. And we look, what we do is we divide minus, and so we look at points from minus infinity to x. So that's the total variation up to x. Okay, so that actually will give us a function of x. And you'll see that this function will be clearly increasing. And what's the function of f? So what do we take points up to x? We partition from minus infinity to x, and we sum the difference of the values of f between these points. But we take the absolute values, that's very important, and so we add up those things. If we go down, still positive. If we go down, still positive. Go up, positive, positive. Okay, so we're looking at how much it varies. A function that oscillate a lot, what's going to happen is this sum's going to blow up, all right? So, and we'll look at the supremum of all the ways of putting points for all n and for all points, n points up to x. Okay, so that gives you a function of x that is increasing. Now, a function said to be a finite or bounded variation if I take x to infinity, this is finite. All right. All right. So these are functions of bounded variation. So let's look at examples. So it seems to be maybe the definition might be abstract, but think always in terms of oscillation. So really, what we're measuring here is the difference of height going up and down. Okay, it's like height can going up and down, but you're just keeping track of the altitude change. Okay, so if the function is increasing and bounded, the total variation of f, let's say on the whole interval, is just f of minus infinity minus f of plus infinity minus f of minus infinity. And this is clear because what happened here, if it's increasing, then when I have here, the absolute value can disappear because the difference is positive. So what you sum is telescopic to end up with the last point minus the first point. And that's what happened here. Okay? So increasing in bound is of bounded variation. So it's not surprising that the variation is the endpoints, the difference of the endpoints. It will always go up. Okay, another important example is if the function is continuously differentiable and the derivative is in L1. Now, if I look at the sum of the absolute value of, so here I wrote t because I'm used to do this for Brownian motion. So let me just erase this. So let's use x to be consistent. Right. And this is x, quad of t there. Alright. So when you sum the absolute value of the difference here, then by Taylor, I can write this as the sum of the difference of the points times the derivative of some middle point. Okay, that's just a mean value theorem. Actually, so I write Taylor, but it's mean value theorem for some point in between. And therefore, when I take n tends to infinity, now I assume that f prime actually exists, yes, and it's in L1, therefore I will converge to the integral of the absolute value of f prime, okay, and which is finite. All right. Okay, so here maybe let's assume also that f prime is continuous, or continuously differentiable. Yeah, that's in the definition here. It's in C1, so the first derivative exists and is continuous. I need that to make sure the point in between converges to a point. All right, okay, so that's for two examples. So another example I will do actually in the live session is a function of an unbounded variation, and the classical function is x sine x to the minus 1. Let's say between minus 1 and 1. So now we can look at variation on a finite interval. It's the same definition. So instead of going from minus infinity to infinity, go from A to B. And I'm looking how much I oscillate in that. Okay, so the absolute value of the increment, or the value of the function. And what happens here is that as you approach 0, you still oscillate quite a bit. Now it decays because of x as you approach 0, but that's not enough. And interestingly, and I'll do that in the example, if you take x squared here, so you have a faster decay at 0, then you have bounded variation. All right, so that's 4 examples in the definition. Now let's construct a sine-Borel measure using this. Now we'll use directly the notes. And here's the most important lemma that's also in Fallen, and kind of condensed it. So if you have a function of bounded variation, let's say on R, and I look at the total variation of f plus f, so remember total variation of f is I can see it as a function. Then these two functions are increasing, and in particular f can be written as the difference of two increasing functions. And this should ring a bell because at the end of the day, remember, the sine measure I can write at nu plus minus nu minus, two positive measure, and we know that positive measure are related to increasing functions. So here's so we're going the right direction. Okay, another thing that is important, so we always need to have right continuity to construct measures. So if f is right continuous, turns out that t of f is right continuous. This I won't do the proof. It's actually in the book. It's just playing with the definition and delta epsilon. And the other thing which is important and kind of obvious is that if you have two functions of bounded variation and you do a linear combination, that's also of bounded variation. Okay, And this is clear just by the definition right here, AF plus BG for some given partition of the interval, okay, and then just took the triangle inequality on F and G. All right. So where are we going to use this? It's just we're going to use this here because T of F is increasing, therefore it has bounded variation, and F has bounded variation. So this guy has bounded variation, and this guy has bounded variation. That's why we need this. Okay, so great. Now, okay, so let's show that these functions are increasing. TF plus F, so we'll just do 1. So if I take y bigger than x, I should have that T of y is bigger than T of x. Now it's just definition of the supremum. I can always find an almost optimal partition xj that is bigger than T of x minus epsilon. And since y is bigger than x, what I can do is, if I look at the variation of y, it should be bigger because that's the sup of the sum of the increment, and then since y bigger than x, I just add the next increment going from x to y. So I always have that because that's also partitioning up to y. And then I add fy here, and I just add up and subtract f of x. Now what we're going to have then is that by so let's just see. So this f of x is here. Let's think about it for a minute. This f of x is here, and I actually chose exactly. So I chose this xj, so that's bigger than tf minus epsilon, and just rewrite that. Okay, and then I have this term that I have to control, but this term is absolute value plus the term inside, so that's always positive, so I can bound that. Okay, so that shows, and that's epsilon is arbitrary, and you're done. Now, clearly the function f can be written trivially like this, and so we wrote f as a difference of two functions that are both increasing, and so you're done. Okay, all right. So where are we? So it's good to go back to the example that I had. So if f is in L1, and let's say f of x is given by the integral from minus infinity to x of f dm. So that's an example where if I take this function, yeah, okay, so this function actually, so what's the total variation in this case? It turns out to be just the integral from minus infinity to x of the absolute value of f dm. And then when I add f of x to that, because I just add the integral inside, I'm going to have absolute value of f plus f, which is 2 times f plus, and if I subtract minus f, I get 2 times f minus. All right, so that's the total variation, and so we're almost done. So remember that the goal today is to relate sign measures on R with functions of bounded variation. So here's the correspondence. So any finite sign measures on RBR gives you a function of bounded variation that is right continuous. And then you have, obviously, since measures are defined by a difference, so the correspondence is up to some normalization, and we choose f at minus infinity is equal to 0. So that's the correspondence between the two. And also it turns out that the total variation of f is equal to the measure which is given by the total variation of f. Okay, so total variation of the measure mu f is equal to the measure given by the total variation of f. That's a bit confusing, but because we're using the same term, but it's because of that relation that we're using the same term. Okay, so let's do the correspondence this way. That's not hard. So if you have a sigma finite measure, Borel finite, so you have the hand-Jordan decomposition, positive and negative parts. Both are regular positive measures. And so it's regular because by construction, remember how we did that for Borel sign measure. And so what happens is that then I can define f plus f minus just by the measure of the set minus infinity x. That's exactly like this CDF, cumulative distribution function and probability. And then we know that by the lemma, the difference of these two functions must have bounded variation because they both have bounded variations. They're increasing. And so we have related the finite sign measure to this to a function f of x by this relation, which is the difference between the two here. All right, that's one way. The other way, if you have a function that is of bounded variation, I want to construct a measure. That's the most interesting case. Then f, as we saw in the lemma, can be written as the difference of two functions, and both functions are right, continuous, and increasing. And you can define actually two measures the usual way, mu plus mu minus, which is the measure given by f plus, and the measure given by f minus. The last thing that we have to see is this equality between total variation of the measure constructed and the total and variation of the function f associated to that measure. And the correspondence is given by this. So I did this exercise in the examples of March 18. That is the total variation of a measure mu we wrote as also, so I'm going to write it as mu plus mu minus of E, right? But another way to write this is to look at the following: the supremum over, also actually here should be an equality. So I look at all the EJ, the joint partition of E, and I sum the absolute value of the measure of this EJ. All right. So that's an exercise with the supremum, and if you have that, this is kind of obvious. So note the similarities with the definition of total variation of f. So in fact, if I have the total variation of f of x, the only difference is that I have, instead of EJ, I just deal with intervals, right? So I have actually less, if you want, it's a supremum over less possibilities, so it has to be smaller than the total variation of the measure mu, as defined here. So that's good. So, and now to have the opposite inequality, how do we do that? So we know the following. So if I look at the measure mu f constructed, the sign measure constructed with f, this is given by f of b minus f of a. If I put absolute value of absolute value, and this has to be smaller than the variation of f, total variation of f at b minus variation at a. Just by definition of total variation, f of b minus f of a is, if you want, just one interval. So it has to be less, just because here I look at how much I oscillate all over the place, and here I just look at the difference between 2 points. And so since I have that for any AB, so here I'll go a bit faster, I can actually this relation extends. These measures are regular because they're so here it's just a positive measure, and here's the difference of two positive measures. So this relation extends to every e, and then you go back up and you use that relation right here. So I have that mu of f of e is smaller than mu tf e. So when I do this relation, use this definition with mu f of e, I get the total variation of mu f. And when I do it with mu of tf, then I get the total variation of utf. So you get the opposite inequality, that actually mu of f, the total variation of mu f is smaller or equal to the total variation of mu of f is smaller or equal to the total variation of it's smaller or equal than the measure given by the total variation of f. Oh, that's confusing. All right, thank you.